Let's continue in 1.2 and define the dot product. We define the dot product in Calc 3 with in 2D and 3D, but now we want to do it in general. So let's let V equal V1 to Vn, W be the vector W1 to Wn, be in or elements of Rn, and then we just define the dot product. Same as before. You do V dot, is how you say it. It's scalar product or dot product equal to, and then is the product of the components. And you add them all up. So it's an operation that goes from a vector a set of vectors, to a real number. So just make a note that that is a real number. All right, so if that's the definition, keep in mind that these are real numbers, each of those. Right, that's the definition of a vector. Right, so each of these components are real. So you get all the properties of real numbers. So you can commute those. You can, if they're the same thing, you know different things happen. So next, let's look at theorem 1.2. No, 1.3. These are properties of the dot product. And in Rn. So all of these are pretty much directly from the definition. I don't think I go through any of these, maybe one. You have the commutative property, so V dot W is equal to W dot V. That's pretty clear because each of these components may commute, so you can commute the whole thing. Oops, didn't mean to do that. 2 is an associative. No, I'm sorry, distributive. U dot V. Oh, I forgot U is there too. So this is a distributive sort of thing. So V, W, and I guess I should have had U up here. So U is also in Rn, same definition. Oh well. U dot V plus W is equal to U dot V plus U dot W. 3, scalar R, so R is a scalar. V dot W is equal to RV dot W, or you can distribute it to the other one. V dot RW. 4, if you have V dot V greater than or equal to 0, and V dot V is equal to 0, that's true if and only if V is 0. 0 vector. 5, and this one, I'm not sure if this is right here, but I wanted to give it to you anyway. The magnitude squared is just V dot V. We've seen that one before too. So we won't look at all those proofs. They're pretty much directly from the definition. So we'll do 5. So 5, pretty straight up, right? I mean, if you just do V quantity squared, that's the square of this square root. V1 squared plus, etc. to Vn squared, and you're squaring that. So that's equal to V1 squared, etc., to Vn squared, which you just separate those out, and you get V1 all the way to Vn, which is just V dot V. Okay, so that's pretty straight, which makes sense. And then we have another theorem that uses those triangles below. I'll bring that up in a second. So this theorem is and I don't know exactly which one it is in the book, so it doesn't really matter. Okay, so this one is the angle between two vectors. So we're going to let theta be the angle between V and W. Now it makes sense in 2D and 3D. 4D, it's kind of hard to maybe talk about an angle between two vectors, but we're just going to say that it exists and then kind of move on. But we'll try to eliminate some of the concepts of angle between two vectors as we go. But this is the one that says V dot W is equal to magnitude V, magnitude W, cosine theta. And then you can rearrange that and have that cosine theta is equal to V dot W over their magnitudes, magnitude V, magnitude W. Somewhere up here, we're going to assume V and W both non-equal to zero vector. Then if you solve for theta, theta is equal to inverse cosine or arc cosine of all of that. So V dot W over their magnitudes, magnitude V, magnitude W. Another result of this is we know that cosine is between -1 and 1. So that means that V dot W is also between -1 and 1. So it's a result we're going to use in one of our next theorems. So to prove that, we're going to use these triangles and this concept. So we'll go through the proof of this. And we want to apply the law of cosine. So let's talk about that. So this will be the proof. And let's recall the law of cosine. So this is the law of cosines. And so if you have a triangle that looks like that, then the square of B plus the square of C is equal to the square of A plus 2 times BC cosine of this angle A. So I'm not going to go through how to prove law of cosines, of course. But we're going to use that and apply it to this triangle with this vector is V, this vector is W. And then you take their magnitudes, and we're going to treat that like B and treat this like C. And then the difference is this. Maybe look that up if it wasn't, you don't remember how to do that, but that ends up being the difference of V and W. Looks like that. And so its magnitude, we'll call that A. And then A, this theta is the angle A. So you could put theta down here if you wanted to. So let's substitute directly into the law of cosines. So you have So first we're going to say, as far as the hypothesis stuff goes, we're going to assume all this is here. So theta is angle between them, V and W are in Rn, and we want to show this part. So we have magnitude V squared, right? So you're squaring those, plus magnitude W squared is equal to the opposite. So magnitude V minus W squared plus 2 magnitude V magnitude W cosine theta. Okay, so that's the law of cosines applied to this triangle. Now, let's take the magnitude V squared and multiply that out. So there's this magnitude of V is the square root of the sum of its components squared, right? So now we're going to square that, and you just get V1 squared all the way to Vn squared. And then you get the same thing for W, so W1 squared all the way to Wn squared. Okay, so that equals, and then you do the same thing for this, those components as well. So you'll have parentheses, V1 minus W1 squared, etc., all the way to Vn minus Wn squared. And just this, actually, I think I'll have room, so let's go ahead and move that down. Use as much room as possible if you'd keep going. Then you would say plus 2 times magnitude V magnitude W cosine theta. Now, this part we're going to expand out and recollect. So when you expand out the binomial, you'll have V1 squared, W1 squared, and in the middle will be 2V1 W1, and it'll be negative. So I'm going to recombine it in a better way, see what you get. So the left-hand side, I'm going to just recopy it. Okay, so I'm going to try to give myself space here. The right-hand side ends up being what? Ends up being V1 squared plus all the way down to Vn squared and then we have the middle terms will be the negative 2V1 W1, and that keeps on going like that, minus ... all the way to 2Vn Wn, and then plus W1, this should be a, no, W1 squared plus ... plus Wn squared. That's when you do this product here, and then everything else in between. And then plus what's left there, 2 magnitude V magnitude W cosine theta. And so look what happens to all these. So this and this will be annihilated. All of these will be gone. These will be gone. I'm going to use all my colors here. These will be gone. And then you just bring over all of these terms to the left-hand side. And so you get 2V1 W1 plus, etc., 2Vn Wn equal to 2 magnitude V magnitude W cosine theta. So now divide out by 2, and you have V1, W1 all the way to Vn, Wn. What is that? That is the dot product, right? There you go. It is the dot product. So you're good. You're done. So left-hand side is the dot product. So left side is the dot product. And so you just get V dot W by definition equal to magnitude V, magnitude W, cosine theta. All right, so we're going to use that in a number of ways. We'll do an example here first and then move on to a couple important theorems. All right, so next, just a quick example to show how to find angle between two vectors. All right, so find the angle. Between between V equal to 1, 2, 0, 2 and W equal to -3, 1, 1, 5. So those are both vectors in what dimension? Those are both in R4, right? So 1, 2, 3, 4. So whatever that means to be an angle, we can still find it because that's just what we'll say it is. So to do that, you need to apply that. So basically, we're just going to do arc cosine of that. So we need to do their magnitudes and the dot product. So let's do the magnitude of V. That's going to be the square root of, what's that, 9? I'll just write it out, I guess. 1 squared, 2 squared, 0 squared, 2 squared, square root of 9, which is 3. Then magnitude W. You don't have to write all these out. -3 squared, 1 squared, 1 squared, 5 squared. 25 plus 9. Square root of 36, which is 6. So these are nice numbers, huh? Do the dot product, V dot W. So basically, you get 1 times -3 plus 2 times 1 plus 0 times who cares plus 2 times 5. So that's going to be 10, 11, 12 minus 3 is 9. So you get cosine theta is 9 over 36, which is a half. So what angle is cosine is a half? Special angle, right? Special angle of pi thirds for cosine. Because cosine's x, right? xy, so pi thirds. So pi, whatever that means for a fourth degree or fourth dimensional vector is pi thirds. Okay. Moving along, definition of, so I put a colon there, so we'll just say definition orthogonal. So what's the definition of orthogonal? Means the dot product is what? Dot product is 0. Yes. All right, so dot product 0 means something more in Rn than perpendicular, right? And we can talk about perpendicular because you get cosine is 0, and that implies that that the angle is pi halves or 90 degrees. But what we really are after, what kind of makes more sense, is the dot product 0, so that you don't have to worry about angles and stuff. All right, so then let's go on to two more really important theorems. The first will be the Cauchy-Schwarz inequality, 1.4 Cauchy Schwarz. Inequality, which can be proved with this theorem above with angles, and we'll do another proof later without an angle. So let V and W be in Rn. Then then absolute value of V dot W is less than or equal to magnitude V, magnitude W. So the absolute value of the dot product is less than or equal to the product of the magnitudes. So let's look at the proof of that. Now this will be a proof using an angle. So we're going to assume theta is the angle between V and W. So we have that V dot W is equal to magnitude V, magnitude W cosine theta. Okay, so if either V or W is equal to 0, we are done. There's nothing else to do, right? Because you get 0. So 0 equals 0 if either of those are 0. So let's assume that's called the trivial case. So let's not worry about the trivial case. They're non-zero. So let's just assume. So this is the we call that trivial case. Okay, so let's then assume they're both non-zero. All right, so if they're non-zero, that's really what we're after. So that's pretty easy, frankly, right? I mean, if you just look at cosine theta, so since absolute value of cosine theta is less than or equal to 1, then this whole left-hand side must be less than or equal to that product. Otherwise, it'll make it smaller, right? So we have absolute value of V dot W, which is equal to magnitude V, magnitude W, cosine theta. That has to then be less than or equal to magnitude V, magnitude W. And that's that's it. I mean, that's what you get when it's when you have cosine in there. So that came really directly from this theorem up here. Just because of that equality you get for angle between them. That allows us to do also the triangle inequality. So I'll do one more. So this is the next theorem. This is called the triangle inequality. So triangle equality says magnitude V plus W is less than or equal to magnitude V plus magnitude W. So let's look at the proof of that. So let's let V and W be in Rn. And let's assume they're both non-zero this time. Just right off the bat. Okay, so otherwise you just get they're both equal to itself or zero, so they're non-zero. So what you do is you look at the square of the left-hand side and then simplify it. So what you do is you look at this square. So you look at v plus w squared. And when you do the same thing squared, it's its own dot product. So now we're using this theorem here. Or not, well, property, I guess. So you have its same thing squared, it's its own dot product. So you get v plus w dot v plus w. And then you use that distributive property, and that gives us v dot v plus 2v dot w plus w dot w. But notice that the v dot v's and are magnitudes. So we can rewrite this as, we can say this is equal to, let's go back to magnitude v squared plus 2v dot w plus magnitude w squared. Now, we're going to keep these the same, v squared and w squared. What we're going to do is apply Cauchy-Schwarz inequality to the v dot w here, which allows us to say this is less than or equal to magnitude v plus 2 magnitude v magnitude w plus magnitude w squared. Right? So this, all of these didn't change. We can highlight those. These didn't change here and here. Let's just keep the highlight going here and here. What changed because of the Cauchy-Schwarz inequality up here, right there, allowed us to do that, allowed us to say this and this. That gives you that inequality. That's the Cauchy-Schwarz. And the 2 just carries along. So then the right-hand side ends up being, that is a perfect square trinomial. So that will factor to magnitude v plus magnitude w quantity squared. And then all you got to do is take the square root of both sides. Square root, and I'll just do my abbreviation for on both sides. And you have the triangle inequality. So therefore, magnitude v plus w is less than or equal to magnitude v plus magnitude w. So the triangle inequality is proved with the Cauchy-Schwarz inequality. Right? That's one of the main aspects of this proof. But the problem with the Cauchy-Schwarz inequality up here of its proof is that we're using angle between the two vectors. So in the next video, I'm going to do a proof of the Cauchy-Schwarz inequality without using the angle. And that'll give us a way to describe the triangle inequality in the end without using angle between the two vectors. So that'll be our goal.